We're almost done taking the Laplace transform of functions, getting into the Laplace transform world. What we will finish up, or what we will start, I guess, and hopefully finish up in this video, is getting out of the Laplace transform world. Untransforming, I say, or unlaplacing, that's not a word. Taking the inverse transform is the better way to say it. So we've got our definition. We've got our definition of the Laplace transform there, transforming a function. We've got our chart that we've been building throughout the other videos so that we don't have to do the integration every time. What I should like to do then is to take the transform of t to the n times a function. Now, I want to show that if I multiply a function in the real world, so a little f of t times t to some power of n, that I get minus 1 to the power of n times the derivative of the Laplace function with respect to s, the nth derivative. Now I know, I promised there were no derivatives in the Laplace world. Well, there are, but not with respect to t. Remember, when we're solving a differential equation using Laplace transforms, our concern is the derivative with respect to time. So if I kind of lied, but not really. There's derivatives with respect to s. So let's actually prove this rule first. We'll start with what happens if I just multiply the function by 1t. That I should just get minus times the derivative of f with respect to s. Well, here's our f with respect to s as our, or expressed as our limit, or sorry, as our integral definition of the transform. And I'm going to just differentiate this with respect to f. So I can unambiguously put f prime, because the derivative in the Laplace world, where the capital F of s is, the derivative has to be with respect to s, because that's the independent variable in the Laplace world. So I'm differentiating this function with respect to s. Well, there's only one s in here. Everything else is t, so everything else is a constant with respect to s. So differentiating just puts a minus s. The derivative of e to the something is e to the something times the derivative of what's up top, sorry, minus t, because t is a constant. So there's f prime, there's the df ds. And I guess because that's a minus sign, I can bring it to the outside. And so now I've got minus this expression. But this expression, let me move this t right in front here. So now the bracketed expression is, that's what you do to take the Laplace transform of t times f. So by differentiating the integral definition, doesn't get rid of the integral because I'm differentiating with respect to s, and the integral is with respect to t. So we've got this rule. So we could say this mumble something by induction to prove this general rule, but what happens every time I differentiate this f of s, what happens? Well, a minus t pops out. If every time a minus t pops out, if I differentiate this n times, there'll be n minus 1s all multiplied together. That accounts for this piece. And here's our nth derivative, which would be ending up putting, every time I differentiate, a t comes down from this chain rule, and I can't take the t outside of the integral because I'm integrating with respect to t. So that's a hand-waving argument for why this particular formula, why this particular transform works. A more rigorous approach would be to prove it by induction. Let's, instead of proving it, let's take a look and we'll do an example. So here's t squared times e to the 2t. So what do we got here? Well, if I'm matching it with this expression, it looks like n is equal to 2, because it's t squared, and it looks like f of t is equal to that e to the 2t. Well, if little f of t is e to the 2t, then big F of s would be the transform of that. That would be the transform of the little f, 1 over s minus 2. So I know what f is with respect to s. I need to differentiate it twice because n is equal to 2. So if I'm differentiating this expression twice, f prime is going to equal to minus this whole bracket squared first derivative, and then the second derivative is going to be a minus 2 is going to come down, so this will be this with the 2. So there's my second derivative. So then the Laplace of this is going to be minus 1 squared, which is just 1. I'm just writing it here for pedagogical purposes, times the second derivative. So there's our transform. And I guess that would just be equal to this piece here. Now, we also can think of it in a different way. We learned in the last video that if I multiply some function by e to the at, then take the transform of that, then I get the shifted f of s. So let's take a look at it. Let's take a look at our example, but in a kind of a different way. So instead of t squared e to the t, I'm thinking of the e to the 2t as the first piece, and the f of t as the t squared. So e to the 2t is matching the e to the at, so a is equal to 2. Then little f is equal to t squared if I'm matching this rule. If little f is equal to t squared, then big F, the transform of t squared, would be 2 factorial over s to the 2 plus 1, or s cubed. So that would be f of s if f of t is equal to t squared. Little f of t is equal to t squared, big F of s is equal to. So then I want the shifted. So everywhere there's an s in here, I want the, so f of s minus 2 would be everywhere there's an s in here, I'm going to put an s minus 2. So I get the exact same thing, obviously. It's just a different way of looking at it using a different rule, but I get the transform of t squared e to the 2t as 2 all over the bracket s minus 2 cubed. How do I connect this to the stuff we were doing when we were talking about eigenvalues? Well, if I got a repeated eigenvalue, let's say a doubly repeated eigenvalue of 2, but there was 3 of them, I would have a constant times e to the 2t, I would have a t e to the 2t, and I would have a t squared e to the 2t. So this sort of thing would show up with a triple eigenvalue of 2. Anyway, let's go to, let's start our unlaplacing. If I Laplace little f and I get big F, we're defining the inverse Laplace as Laplace to the minus 1 of the big F. This I get equal to the corresponding little function. So I'm going to be using this table backwards. There, I don't have a definition, a brute force integral definition that I can use. So I'm going to have to set things up when I have a problem to unLaplace. I'm going to have to set things up so that I can see little chunks of my problem in the transform chart and then use the chart backwards. If I were to see, 2 over s cubed, I could write t squared, for example. So let's see. Oh, well here I've got, I'm taking the inverse transform of 7 over s to the fourth. If I go up to my chart, s cubed s to the fourth, that looks like I should be using this rule. This looks like this rule where the n plus 1 is 4, so n is equal to, it looks like n is equal to 3 in this case. So if I were to take the transform of t cubed, I'd get 3 factorial 6 over. So I don't have a 6 on the top. So what I'm going to do then is I'm going to factor that 7 out. I'm going to put it on top of a balancing 6 and make now the 6's cancel, but this piece now matches this piece exactly when n is equal to 3. So the inverse Laplace then, or little f of t, would be equal to, this is just a constant, so it stays, times t cubed. So in other words, that's equal to the inverse Laplace of 7 over s to the fourth. So the only thing that was that we had to balance was we needed that 6 on the top. So I multiplied top and bottom by 6 over 6. This 6 is there to match the formula. That's the balancing constant. This next one, okay, if I'm, oh, well, this matches, I'm using this rule here. From the chart. Let's take this 7 to the outside, and that just puts a 1 on top. Put that back down. So now, when I take the inverse Laplace, 7 times, it looks like a is equal to 3, e to the 3t. That one's pretty straightforward. So I can recognize the 1 over s minus 3 as something that would connect to an eigenvalue of 3. Next example. Oh, I've got the brackets squared. That makes me think of what we had just done here at the end. We had a bracket cubed, a bracket cubed. So I could use either of these rules. I could transform it with like t something times e to the, or e to the. I think what I'm going to do is I'm going to use this rule here. I could choose either. So if I match this rule, then I see this as, it looks like a is equal to 3. That means f is just the regular f of s, not f of s minus 3, must be equal to the 7 over s squared, which would unlaplace to be on its own. So if capital F of s was 7 over s squared, then what would Laplace into that? That would be 7 t. So I want then, therefore, the inverse Laplace this expression should be equal to e to the 3t times our 7t. And I guess I would probably write that as 7t e to the 3t. I could have got the same result if I would have approached this and saw it as not the shifted not this shifted f of s, but saw it as the derivative of 1 over s minus 3. Now my Laplace function, my f of s is 1 over s squared plus 9. Okay, 1 over s squared plus 9. That looks like, with the plus on the bottom, s squared, that looks like my cosine. Oh wait, no, because the cosine has an s on top. It's just a number, no s on top. So this looks like my sine. So I'm thinking about this rule here. It looks like b is equal to 3 to match that rule. But in that case, I would need a 3 up top. So I'm going to fix that. I'm going to put a 3 on top and multiply the whole thing by a third. So my question's the same, but now this matches my rule when b is equal to 3. So that means little f must be equal to the third, that's just there as a balance, sine 3t. Oh, this next one does have an s. So the only difference, I'll go up here and look for the, from my chart, that's the cosine one. The nice thing about the cosine one is I don't have to balance it. It's supposed to be an s, there's an s, b is equal to 3, so we can just write this one down. That's going to be cos, no balancing needed, 3t. Done. What about this 1 over s squared minus, the purpose of this example is you're supposed to, as a student, say, oh, this is going to be a number and there's a, an s squared and a 9. I'm going to think about the sign. And then me as an instructor, I'm going to say, no. The bottom of this, the denominator of this function is factorable, so you should factor it. The trig only shows up when there's an unfactorable quadratic. In fact, this unfactorable quadratic, this s squared plus 9, if it was lambda squared plus 9, if that was the auxiliary equation, you would get eigenvalues of plus or minus 3i. So you'd get pieces that would be a number times sine 3t and a number times cos 3t. But here, if this s squared minus 9 was a lambda squared minus 9, if that was the eigenvalues, if that was the auxiliary equation, then you'd factor it. So I should factor it. When I do factor it, I can see that the eigenvalues, if this was an auxiliary equation, should be 3 and minus 3. So I expect to get pieces that are e to the 3t and e to the minus 3t. I need to break this up with partial fractions, which I guess I would write as 1/6 times that minus 1/6. So I'm just breaking this up into partial fractions. And now I can unLaplace it. It's going to be 1/6 times the e to the 3t minus 1/6 e to the minus 3t. I'm using the same rule I used here, this taking the Laplace of e to the at is 1 over s minus a. Here the a is negative 3, here the a is 3. Two more examples. This next one, well, this quadratic is an unfactorable quadratic, so I can't factor it, it's unfactorable. If I were to if this was the auxiliary equation and I would be looking for roots, let's actually just do that. I'm going to solve this. So if this was the auxiliary equation, I would get roots of 2 plus or minus 2i. That means I expect to get pieces that would be e to the minus 2t cos 2t e to the minus 2t sine 2t. I expect those pieces of algebra. So this solution is really just me finding out the roots of the characteristic equation. So we sort of know where we're going with that. I need to complete the square. That's the piece of algebra that I got to do here. So in completing this square, that's going to be s minus 2 squared, no, plus 2 squared, plus 4. If I were to square all this out, there would be a plus 4 and another plus. So I've completed the square. Now, this looks like 1 over, it looks of the form 1 over s squared plus 2 squared. So it's making me think 1 over s squared plus 2 squared. It's making me think about a sign here. But I need this to be a shifted sign because it looks like the sine function with an s plus 2 stuck on it. So I'm going to use this rule. And I'm thinking about this rule where a is equal to 2. No, a is equal to, because it should be a minus, a is equal to minus 2. So I'm thinking about that. That's the rule I'm thinking about here. So if f of s plus 2 is equal to this expression, then f of just plain s should be equal to 1 over s squared plus 4. If f of s is, capital F of s is 1 over s squared plus 4, and if I was going to unLaplace that, that looks like this expression here, but I need a b on top. I need a 2 on top. So I'm going to do the same thing. I'm going to balance it by multiplying by 2 over 2. So now I can unLaplace this expression, find out what little f of t is. It's going to be that half. This is just like this example, except for instead of 3, it's 2. So this will be sine 2t. So now I know what little f is. So let's go back here. I know what little f is. Oh, so I can take the unLaplace. It should be, when I unLaplace this piece, so let's write this as inverse Laplace of e to the minus 2t times, no, my bad, taking the inverse Laplace of this expression is equal to e to the 2t, e to the minus 2t, times 1/2 times the f of t times the 1/2 sine 2t. Now this is one of the cases where, for sure, don't just watch me do math and then, turn the video off and say, I'm done. Actually repeat, go through, complete the square. This is going to be an important part. You're probably going to need to do this piece somewhere for grades. But take a look at this. This expression that I get is like what I expected. If I showed you this, probably I would write the half on the outside, right? But if I showed you this, you could see, oh, that looks like an eigenvalue of minus 2 plus or minus 2i, which is what we got when we were thinking of the denominator of this expression as the auxiliary equation. If I take the Laplace of this and simplify everything down, I should end up getting this original expression. One last example. It's got a unfactorable quadratic on the bottom and a line. So our first step is I'm going to complete the square with this to break it up into pieces. Pieces that I can match with the chart. So I break this up and clean this up a little bit here because And I think I'm going to take a fifth out of the front of this as well. So when I do partial fractions, there's what I get. I can unLaplace this piece, no problem. That's going to be a fifth e to the minus 2. This one, though, this looks like a combination of, I'm going to break it up over this minus sign. So let's bracket that for pedagogical purposes. I'm breaking it up over this minus sign. So there, now this piece with a number over s squared plus 4, I'm going to do with a sine, and this piece with an s, we're going to do with a cosine. So if I'm going to do this piece with the sine, it looks like b squared is 4, so b is 2. I'm going to take this 6 to the outside, put a 2 on the bottom, and a 2 on the top. So now this piece matches exactly our b over s squared plus b squared. Yeah, this 6 over 2 can clean up to be a 3 in a minute, but let's unLaplace everything. We're going to have 1/5, that's just a constant, e to the minus t, that's this piece inverse Laplace, minus 1/5. This first piece is set up nicely for cos 2t, and then minus 3, if I cancel this 6 and this 2, sine 2t. And I can multiply that fifth through if I want and get, what do I get? I get a number times e to the minus t, I get a number times cos 2t, and I get a number times sine 2t. If I looked at this and asked you what the eigenvalues were, you'd say it looks like a plus or minus 2i for the trig and a minus 1 for this exponential. If I thought of this bottom as the auxiliary equation, found the roots of it, those are the roots I would get, minus 1 and plus or minus 2i. Now, it's all practice on your part.